Hi everyone, so this is my presentation for the machine learning project as a part of the Coursera course titled Machine Learning Foundations for Product Managers. So I'll be walking you through this presentation as well as a short demo of sorts. So the task in this project was to create a machine learning model that can predict the output or energy output of a power plant given certain data points. The data points or the data set that was shared with us to carry out this project had four input features. So temperature readings, ambient pressure readings, humidity, and exhaust vacuum. And it had one output or the target variable which our model attempts to predict, which is the hourly electrical energy output from this power plant. Maybe it helps to see how the data looks. So let me just open up the data set, which is in the form of this CSV file, and it looks something like this. The headers here are abbreviated, but these are the same four features that I mentioned, the temperature, pressure, humidity, and so on. And PE is the target or the output variable, which represents the energy output of the power plant. Um, so a bit detail of the problem description, what we are trying to achieve. So this is basically a supervised learning regression modeling task. So our model tries to predict the value of our target variable, which is the energy output. Um, and I've decided to use the linear regression algorithm to carry out this modeling task. Linear regression is one of the simplest algorithms to carry out such regression prediction type tasks. It assumes linear relationships between the input and the target variables and tries to obtain like a formula of sorts to describe the relation between input and output. The formula for a linear regression looks something like this. Coefficient 1 into input feature 1 plus coefficient 2 into input feature 2 dot 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 and some constant term. So in this example, if you see y is our target variable, x1, x2 would be values of the input features to which we multiply by different coefficients or weight values, and there is some constant which together then establishes the relationship. The aim, of course, of the model is to obtain the coefficient values, so W1, W2, and so on, that captures the relationship between y and the x's. So for this exercise, I decided to create two models, and then the idea is to compare the two models so that we can choose the best one. Yeah. So we will use two models, both using the linear regression algorithm. But in model one, we use only three of the input features. So these are features that I chose um, pretty much randomly. So I'm choosing in model one temperature, exhaust vacuum, and relative humidity. And model one will then use only these three to sort of find the linear regression, um, the formula. And in model 2, we use all four of the input features, temperature, exhaust vacuum, relative humidity, and ambient pressure, and use all the four values to come up with the formula that I just mentioned about. Of course, we want some way to compare the two models, and one of the most common output metrics for any linear regression based algorithm is to use the mean squared error, which is a measure of the average of the square of the error or difference between the actual target variable value from the data set versus the predicted value by our model. um, and we use MSE value for each of our models, and then the model with the lowest MSE value will be chosen, of course, because that's giving us the least error. Data sets. So in general, it's a good practice to always split your available data into a data set used for training the model, and then a separate data set called the test data set used to test or evaluate the performance of your model. This allows for us to evaluate the performance of a model on data that the model has not seen before while it was being trained. And yeah, that's considered as a good practice for any machine learning project. So in this project, what I've done is we had total of 9,568 observations. So I took roughly 958 observations, so close to 10% of the observations as our test set. So I just wrote up a small script to randomly pick 958 rows from the original data set and um, converted that into my test set. The remaining data became my training plus validation data. So basically, it's entirely the training data, but we split it up into further two sets, which is training, which is about 80%, and 20% for validation. So I'll go through why we do that in uh, remaining of my presentation. But basically, the data set is divided into three sets now, which is training, validation, and test set. So now let's go through our approach, and at each step, I'll try to also show the the Excel models. So by the way, I've decided to use the regression function that MS Excel offers, and that is good enough to perform basic linear regression based models. I'll show you shortly how to do that. So we have to go through the following steps. We have to train each model. So we have two models, which means we have to run the regression function in Excel on the training data and capture the mean squared error for each of the models. Yeah. So let's go into model one, and this Excel is containing the training data. Yeah. So if you see the data here, just scroll all the way up. So this is subset of our original data set, and this is I'm considering to be the training data, and it has all the four input features and the target feature. What we have done is by running the regression um, regression tool that is provided by Excel, and the output is on the other sheet here. Wait, sorry. Switch to the second sheet, and this is the output of the regression function, and I've highlighted some key elements of this output. One of the main things that we are interested is that in this regression modeling for our training dataset, we are getting a mean squared error of 20.67. That's for model 1. And these are the coefficients that this model has come up with. So these are the W1, W2 values, if you recall, that will act as the multiplying factor for each of these input features, so temperature, exhaust, and humidity, and so on. Intercept is the constant value, which is the C in the linear regression equation. So this model is telling us to use these as the coefficients, and this is the mean squared error. At the bottom here, we can also see the for each of the observations or each of the rows, what was the predicted value and the residual, which is the difference between actual value, which is present in this column here, versus the predicted value by our model. But for now, let's just keep this number in mind. 20.67 is the model 1's mean squared error. So we do the same thing with model 2. By the way, before we jump to model 1, if you see here, this model only has three of the four input features, which is what we are after, because this model, after all, decided to use only three input features, and hence it just has three elements, let's say, to the linear regression equation. We now look at model 2, and for model 2, if I open the similar Excel, now this is the training only data set for model 2. So if you look at it, it has this same training data set, and what we have done here is yeah, so we have run the similar regression model here, and we have obtained a model with close to the same mean squared error. So the previous one was 20.6 something, and this is 20.58. So fairly close to each other in terms of the mean squared error. And these are the coefficient values that this model has come up with. So these are the multipliers, the W1, W2, W3, W4 for each of our input features. And this basically forms the basis of our linear regression equation. So based on this, what we have now so far is that after this step, which is training, model 1 gives us a mean squared error of 20.67, and model 2 gives us mean squared error of 20.58, which means that model 2 is slightly better with a lower MSE. So the next step is then we take these two models, or the formulas which these two models have given us, and apply it on the validation set, and then capture the MSE values for both the models. We do this with the hope that the mean squared error remains fairly the same, or at least doesn't go worse, because this is a new data set that the model hasn't seen before. And yeah, we have to see how the model behaves now on the new data set. So this is the validation only data set for model 1 again. Just a reminder, so this is the model which considers only three of the input features. So let me scroll all the way to the top. And if you see here, this is of course the data set, the validation data set. And over here, I've added some new columns here. What are these now? So model 1 predictions column is basically applying the linear regression equation that we got from our training step, and applies it to the data set here. So if you can see, it's multiplying temperature by some coefficient value plus the exhaust by some other coefficient value, and so on. Plus it's adding on the constant value. And based on this, the model 1 generates these predictions all the way to for each of the rows here. The next column here is the difference between the actual value, which is part of the data set, and the model prediction. So this is basically just a subtraction of the E column and F column values. What we do next is do a square of these values. So this is just the G column values raised to the power of 2. And this is our the squared error, basically, or squared difference. Now, if I scroll all the way down to the bottom, this is now the summation of all of these squared errors, divided this by the number of observations we have in this set, which is 1723. We get 23.66, which is the mean squared error value for model 1 on the validation dataset. So just jumping back here, for model 1, originally on the training data, we got mean squared error of 20.67, and now we have a slightly worse performance with the MSE value of 23.66. Let's see how model 2 did on the validation data. So I open this up, and we have a similar thing here as well. So this is the same validation data set, model 2 predictions. Now model 2 uses A2, B2, C2, and D2. Four input features and multiplies each of it by a different coefficient, which are the coefficient values we obtained during training. And that's basically the linear regression formula, yeah. And it obtains these values. Similar exercise, I obtain the difference between actual and predicted values here. So that's just a subtraction between column E and F. I get the square of the residual or the difference, which is just the G column values powered to 2. And after obtaining all of these squared residual values, I sum it up, divided by the number of observations we have in this data set, 1723, which gives us the mean squared error for model 2 on the validation dataset, which is 36.82, which, as you will see, is a lot worse. So from 20.58, we have now gone to 36.82. So on our validation dataset, the model 1 performed way better. So the conclusion here is then, at step 1, the mean squared error of both the models were fairly close together, like 20.67 versus 20.58, although model 2 was slightly better. But over the validation data now, model 1 is way better than model 2. So I'm inclined to choose model 1 as the winner here. And the next step now is to retrain model 1 against the entire training and validation dataset. So we basically now take both the training and validation dataset and retrain model 1, which is using 3 out of the 4 features, and yeah, try to get the new updated coefficient values. So going back here, model 1 is the best model we have chosen so far. And on both training and validation data set, what we now do is rerun the regression. So in this tab, we have the entire training and validation data set, all of the values here. This still doesn't contain the test data set, mind you. And when we run the regression function here, we get this output. We get the coefficient values, of course, the new ones, and we get a mean squared error updated value of 20.99. So this is, let's say, model 1's final mean squared error on the entire training and validation dataset. So 20.99 is the final MSE, let's say, of our model 1, and we are now good to validate this model against our test dataset. So let's see how that went. And here we have the test data set. So this data set is much smaller, as I mentioned earlier, about 958 rows here in the test data set. It has all of the input variables and the target variable, but model 1 only uses three of these variables. So the formula, of course, here uh, is taking into account the updated coefficient values that we got from the previous step and the updated constant value, of course. And based on this, these are the model's predictions. And compare that with the actual data from this test data set. These are the residual values that we get. So again, similar difference between actual and predicted values. We also get the squared of the residual values here. Scrolling down to the bottom, we get the sum of all squares of the residual or the difference values, and we divide that by the number of observations, which is 958 or 957 rather, and this is the residual or the final rather MSE, mean squared error, that we get for our model 1, which is a lot less than any of the previous mean squared error values that we got. So this leads me to believe that model 1 is doing a fairly good job of predicting based on the training data and the test data that we have obtained. I hope that was clear enough, and yeah, thank you for listening.